In this video, we'll cover water ionization. Water ionization is related to acid and base like the previous video. Now, water with another water, we don't really think about them reacting together, but there is a very tiny reaction that's going on. What's that reaction? Well, if you look over here, here is water molecule, and on the right is another water molecule. The hydrogen from this left gets plucked out and it gets attached to this water, forming into a hydronium ion. As you can see on this side then, this H2O becomes an hydroxide ion. Knowing this, we can apply the Bronsted-Lowry definition and label the acid, base, conjugate acid and base because you see the transfer of hydrogen being donated from one point to another. Since this water is the one that is donating the hydrogen, we will consider this as the acid. Since the one in the blue is the one that is accepting the hydrogen, we'll consider this as base. Therefore, the base now becomes its counterpart, which is conjugate acid. Again, this water acid becomes an hydroxide ion. It's OH minus, there's H is gone. So now we have conjugate base. Just in case you forgot, I will let you know that this is called the hydronium ion, and this is hydroxide ion. Name could get pretty confusing. But I do want to show you the chemical formula, not this expanded form, but in the chemical formula, you notice that there is aqueous in the hydronium ion and the hydroxide ion, and liquid in the water. Well, we can then we can produce an equilibrium constant for this particular reaction. We know that in the equilibrium constant, we always need a product on top and a reactant on the bottom or the denominator in order to find the equilibrium constant, as long as they're either gas or aqueous. So for equilibrium for K, we know that product is the concentration of hydronium ion and concentration of hydroxide. That goes on the numerator. What about the denominator? Well, denominator, we want to put the reactant there, but you'll notice that the water are in liquid form. If it's in a liquid form, then we don't put it in the equilibrium constant. So equilibrium constant for this water ionization reaction is just this. In fact, we put a little W next to the K in order to let you know that this equilibrium constant refers specifically for water, so W water. In the next slide, you will see that same equation here, but you'll also see the actual value of Kw. This is 1.0 times 10 to the negative 14. Very, very small value. Now that we know the value, we can do some calculation in the learning check. But before I start to move on, just know that when this reaction does occur, the concentration, they're all in 1-to-1 ratio. So meaning the concentration of acid and the concentration of hydroxide, when it's in equal format, like a pure water form, then that is equal. These two values must equal in order to form 1.0 times 10 to the negative 14. Let's do a learning check based on what I have just said so far to get some clarity. So here, what are the hydronium ion concentration and hydroxide concentration in pure water? So we know that Kw is equal to H3O plus. That's your hydronium ion concentration, and hydroxide is OH minus. In pure water, the concentration of the hydronium and hydroxide are exactly the same. So that means this is X, and then this must be X. Kw we already know the value for, which is 1.00 times 10 to the negative 14 is equal to x times the x. X times x is x squared. And in order to get rid of the square, we're going to square root both sides. If you plug this into the calculator, you'll notice that x is equal to 1.00 times 10 to the negative 7. And that means this is a concentration of, I should put molarity of H3O plus, which is the same value for hydroxide. Let's do a next learning check. A solution of acid in water has hydronium ion concentration of 2.0 times 10 to the negative 6 molarity. What is the concentration of hydroxide ion at 25 degrees? So we know that Kw is equal to 1 times 10 to the negative 14. We also know hydronium ion concentration based on the given problem, which is 2.00. I should put 2.0 times 10 to the negative 6. And then we have hydroxide, which is what we're looking for. And we have the equation Kw is equal to the hydronium and hydroxide. So let's go ahead and divide hydronium ion both sides. So Kw, and then, here, let me cancel this out first, okay? Kw all over hydronium ion concentration is equal to hydroxide. Now we can add some values in and then try to solve for hydroxide concentration. So Kw is, I'm going to rewrite this up here, 1.00 times 10 to the negative 4 all over 2.0 times 10 to the negative 6. That would give me the concentration of OH minus. And if you were to plug this into the calculator, you would get 5.0 times 10 to the negative 8 as hydroxide concentration in molarity. So that's your final answer. So something to note now before you move on to the next video is that in any substance, okay, whether it's acid that is in water or if it's a base that is in water, it's going to start to play around with the the hydronium and the hydroxide concentration. That's where things are going to shift back and forth. And it is that particular value that we can determine if a solution is acidic, very basic, and so on and so forth. It's, again, the hydronium ion and the hydroxide ion that's going to help you in the next few videos in determining how acidic a solution is.